Close your eyes for a moment and imagine holding a perfect crystal in your hand. 6 smooth sides rise to meet at elegant pyramid points on each end. Light catches within its depths, refracting through transparent walls that seem almost too pure to be real. This is quartz, a mineral so fundamental to our world that it literally runs through the veins of our planet and powers the device you're using to watch this video right now. Quartz is silicon dioxide, with the beautifully simple chemical formula SiO2. Just 2 elements, silicon and oxygen, arranged in an endlessly repeating pattern to create one of nature's most remarkable materials. What makes this even more extraordinary is that these are the 2 most abundant elements in Earth's crust. Oxygen makes up about 46.6% of the crust by mass, while silicon accounts for approximately 27.7%. Together, they form the partnership that builds not just quartz, but the very foundation of our rocky planet. As the 2nd most abundant mineral in Earth's continental crust, surpassed only by the feldspar group, quartz comprises approximately 12% of the lithosphere by mass. If you've ever walked on a beach, you've walked on quartz. Those countless grains of sand beneath your feet, most of them are quartz, weathered and worn by millions of years of wind and water, yet still maintaining their essential character. The mineral's extraordinary resistance to weathering means it outlasts nearly everything else, accumulating in riverbeds, beaches, and desert dunes across every continent on Earth. But quartz is far more than just pretty rocks and beach sand. This is the mineral that quite literally keeps time in our modern world. Inside nearly every watch, smartphone, computer, and digital device sits a tiny sliver of quartz, vibrating with absolute precision to mark out the seconds of our lives. The piezoelectric properties that make this possible, the remarkable ability of quartz to convert mechanical pressure into electrical voltage and vice versa, weren't discovered until 1880. Yet they've since revolutionized everything from sonar to surgery. The story of quartz is one of humanity's longest relationships with any mineral. Our earliest ancestors, living more than 2.5 million years ago, shaped quartz and its closed relative flint into the first tools. They chose it carefully, recognizing that while quartz would fracture to create sharp edges for cutting, those same fractures followed predictable patterns that allowed skilled hands to create exactly the tool they needed. This wasn't random stone smashing. Archaeological evidence suggests our distant ancestors understood the material properties of quartz with remarkable sophistication. Ancient civilizations saw something more than utility in quartz crystals. The ancient Greeks believed clear quartz was ice, permanently frozen by the gods, so perfect in its clarity that it could never melt. They called it crystallos, meaning ice, and from this word we get our modern term crystal. Roman naturalist Pliny the Elder, writing in the 1st century, documented the Roman fascination with quartz. Wealthy Romans carved cooling spheres from clear quartz to hold in summer, fashioned drinking vessels from it, and paid extraordinary sums for perfect specimens. One Roman woman reportedly spent 150,000 sesterces, equivalent to 50,000 measures of grain, for a single crystal ladle. In China, quartz held a place of reverence for over 7,000 years. Called water jade by the Chinese, clear quartz was believed to be water that had frozen for thousands of years and would never thaw. Prince Liu Sheng was laid to rest in 113 BCE, wearing a burial suit made of 2,498 pieces of jade, stitched together with gold thread, and quartz sand was used to polish each piece to perfection. The Japanese saw quartz crystals as the physical embodiment of dragons, not the European serpents of myth, but the wise, benevolent dragons of Asian tradition. A crystal sphere represented the heart of a dragon, holding its power, wisdom, and purity. Temple carvings throughout Japan depict dragons clutching crystal balls, and Japanese mythology describes smaller rock crystals as the congealed breath of the white dragon, while larger specimens were the saliva of the violet dragon. Today, we understand quartz through the lens of crystallography and solid-state physics rather than mythology. Yet the mineral has lost none of its power to fascinate. We've learned that those ancient observers weren't entirely wrong. There is something almost magical about quartz, though the magic lies in its atomic structure rather than divine intervention. The perfect hexagonal symmetry of quartz crystals emerges from the arrangement of atoms too small to see, each silicon atom bonded to 4 oxygen atoms in an endless 3-dimensional lattice of extraordinary strength and stability. This same structure gives quartz a hardness of 7 on the Mohs scale, making it harder than steel but softer than topaz. It allows quartz to transmit not just visible light but ultraviolet radiation, a property rare enough to make high-purity quartz invaluable for scientific instruments. The structure creates the piezoelectric effect that powers our digital age, and it produces an astonishing range of colors through the incorporation of tiny amounts of impurities. Iron creates purple amethyst. Aluminum and lithium produce pink rose quartz. Natural radiation combined with aluminum forms smoky quartz's brown hues. From the beaches, where sand grains tumble in surf, to the high-tech fabrication plants, where semiconductor wafers are grown in crucibles made of ultra-pure quartz. From the depths of Earth, where crystals form over millions of years, to the laboratory, where synthetic quartz grows in days, this mineral connects the deepest past with the cutting-edge present. In the next hour or so, we'll explore 100 fascinating facts about quartz. Facts drawn from geology, history, archaeology, physics, and technology. We'll discover how this simple compound of silicon and oxygen has shaped human civilization and continues to be absolutely essential to our modern technological world. So settle in, get comfortable, and let's begin our journey into the crystalline world of quartz. To truly understand quartz, we need to descend to the atomic level, to the realm where silicon and oxygen atoms dance in precise geometric patterns. The arrangement is deceptively simple in concept, but profoundly sophisticated in execution. Each silicon atom sits at the center of a tetrahedron, a 3-dimensional pyramid shape with 4 triangular faces. At each of the 4 corners of this tetrahedron sits an oxygen atom. Now here's where it gets interesting. Each oxygen atom is shared between 2 silicon tetrahedra. Imagine 2 pyramids meeting point to point, the shared corner being a single oxygen atom that belongs to both. This sharing creates a continuous 3-dimensional framework that extends infinitely in all directions through the crystal. This silicon-oxygen framework is what gives quartz its remarkable strength. Unlike minerals that rely on weak bonds between layers, minerals that cleave easily, like mica, quartz's structure is strongly bonded in all directions. When you try to break quartz, the crystal doesn't split along neat planes. Instead, it fractures with what geologists call conchoidal fracture, creating those distinctive curved shell-like surfaces that our Stone Age ancestors exploited for toolmaking. The formula SiO2 tells us that for every silicon atom, there are 2 oxygen atoms. But because each oxygen is shared between 2 silicon atoms, each silicon effectively has 4 oxygens, and each oxygen has 2 silicons. The ratio works out perfectly, and the structure extends seamlessly in all directions. Now, quartz exists in different forms depending on temperature. And this is one of those facts that reveals how dynamic crystals really are. At normal temperatures, the temperatures we experience at Earth's surface, quartz crystallizes in what's called the trigonal crystal system. This is known as alpha quartz or low quartz, but heat quartz above 573 degrees Celsius, and something remarkable happens. The crystal structure rearranges itself into a different configuration called beta quartz or high quartz, which belongs to the hexagonal crystal system. This transformation happens suddenly and completely at that specific temperature. It's not a gradual change. It's a phase transition, similar to how ice suddenly becomes water at 0 degrees Celsius. For potters and ceramicists working with quartz-bearing clays, this transition can be problematic. When quartz in a ceramic piece transitions from alpha to beta or back again during firing or cooling, the sudden structural change can cause the piece to crack. Understanding this phase transition is crucial for anyone working with quartz at high temperatures. The ideal quartz crystal, one that has grown without interference in a perfect environment, takes a specific, easily recognizable form. Picture a six-sided prism, with each face being a long rectangle running parallel to what crystallographers call the C-axis. At each end of this prism, the crystal terminates in six-sided pyramids. If you've seen photographs of large, well-formed quartz crystals from places like Arkansas or Brazil, you've seen this classic shape. The angles between the prism faces are always exactly 60 degrees. Always. This constancy of angles was first recognized by Nicholas Steno way back in 1669, and it became one of the foundational principles of crystallography. The fact that quartz crystals always maintain these 60-degree angles, regardless of how distorted or malformed the crystal might otherwise be, tells us something profound about the underlying atomic structure. The angles reflect the geometric arrangement of atoms, and no matter how quickly or slowly the crystal grew, no matter what impurities it incorporated, that fundamental geometric relationship remains constant. But here's where quartz becomes even more fascinating. The crystal structure is chiral, meaning it has handedness. Just as your left and right hands are mirror images but cannot be superimposed on each other, quartz crystals come in left-handed and right-handed versions. The atomic spiral that runs through the crystal structure can spiral to the left or to the right. Under a microscope, if you know what to look for, you can identify whether a quartz crystal is left-handed or right-handed by examining certain small crystal faces that appear only on one type or the other. This chirality, this handedness, is absolutely essential for the piezoelectric properties that make quartz so valuable in electronics. A centrosymmetric crystal, one with a center of symmetry, cannot be piezoelectric. The asymmetry of quartz's structure is precisely what allows mechanical pressure to separate positive and negative charges within the crystal, generating a voltage. Most natural quartz achieves remarkable purity. Well-formed crystals typically contain more than 99.5% SiO2. But for high-technology applications, even this isn't pure enough. Semiconductor-grade high-purity quartz must contain less than 50 parts per million of impurity elements. At these purity levels, quartz commands prices around $10,000 per ton, a far cry from ordinary sand. The quest for ultra-pure quartz has led to intensive mining in only a handful of locations worldwide. The spruce pine deposits in North Carolina produce quartz so pure that it has become essential to the global semiconductor industry. These deposits formed 380 million years ago and contain quartz with impurity levels measured in parts per billion rather than parts per million. The crucibles that hold molten silicon during the manufacture of computer chips require this level of purity. When we talk about quartz's physical properties, the hardness of 7 on the Mohs scale deserves special attention. This scale, developed by Friedrich Mohs in 1822, ranks minerals on their ability to scratch other minerals. Quartz defines the 7 position. It will scratch anything softer, including window glass and steel knife blades, but can be scratched by anything harder, such as topaz or corundum. This specific hardness made quartz ideal for countless applications throughout history. Hard enough to maintain a sharp edge, but not so hard that it was impossible to shape. The density of quartz is 2.65 grams per cubic centimeter. Not particularly heavy, but denser than water. This density, combined with quartz's resistance to weathering, is why gold prospectors learn to look for quartz veins. Gold, with a density of 19.3 grams per cubic centimeter, would settle out of eroding quartz veins and accumulate in stream beds, leading prospectors back to the source. Quartz's optical properties are equally remarkable, with refractive indices of 1.544 for the ordinary ray and 1.553 for the extraordinary ray. Quartz is birefringent, meaning it splits light into 2 rays traveling at slightly different speeds through the crystal. This property, called double refraction, can be observed in clear quartz crystals and is used in various optical instruments. Perhaps more importantly for modern technology, quartz transmits ultraviolet light. Most glasses absorb UV radiation, but high-purity quartz transmits wavelengths down to about 170 nanometers. This makes quartz essential for UV spectroscopy, UV sterilization equipment, and photolithography in semiconductor manufacturing, where UV light is used to etch incredibly fine patterns onto silicon wafers. The melting point of quartz is 1710 degrees Celsius. At such extreme temperatures, quartz doesn't actually melt into a liquid in the conventional sense. Instead, it forms a glass, an amorphous solid, without the regular atomic structure of crystalline quartz. This is fused quartz, or fused silica, and it has its own remarkable properties. Fused quartz can withstand continuous operating temperatures up to 1150 degrees Celsius, making it ideal for laboratory glassware, telescope mirrors, and high-temperature industrial applications. The thermal expansion coefficient of quartz is remarkably low, about 0.000059 per degree Celsius. This means quartz barely expands when heated, a property that contributes to its stability in oscillators and its usefulness in precision instruments. However, this low thermal expansion is also why quartz crystals can shatter if heated too quickly. The outside tries to expand while the inside is still cool, creating stresses the crystal cannot withstand. Natural quartz crystals can also contain inclusions, other minerals trapped inside during growth. Some of these inclusions create spectacular effects. Rutilated quartz contains needle-like crystals of rutile, creating golden threads through clear quartz. Tourmalinated quartz holds black tourmaline needles. These inclusions tell stories about the crystal's formation, recording moments when other minerals were present in the crystal-growing solution. The atomic structure of quartz also explains its piezoelectric properties, though we'll explore those in more detail later. For now, it's enough to understand that when pressure is applied to a quartz crystal in specific directions, it causes tiny displacements of silicon and oxygen atoms. These displacements separate positive and negative charges, generating a voltage across the crystal. The effect is reversible. Applying a voltage causes the crystal to deform mechanically. This bidirectional property is the foundation of quartz oscillators, sonar, ultrasound, and countless other applications. Understanding quartz at the atomic level transforms it from simply a pretty mineral into something far more profound, a window into how nature builds structure from chaos, how geometric patterns at the atomic scale create properties we can observe and use, and how the simplest chemical formula can give rise to extraordinary complexity and utility. The silicon and oxygen atoms that make up quartz are common, but their arrangement is anything but ordinary. While perfectly clear, colorless quartz is beautiful in its purity, nature has found countless ways to paint quartz in nearly every color imaginable. These varieties range from transparent to opaque, from common to extraordinarily rare, and each has its own story written in the impurities and conditions of its formation. Let's begin with amethyst, probably the most beloved colored variety of quartz. That rich purple color has captivated humans for thousands of years. The ancient Greeks knew it well and gave it a name derived from amethystos, meaning not drunken. They believed, whether seriously or hopefully, that drinking wine from an amethyst cup would prevent intoxication. Soldiers wore amethyst amulets, believing they would keep clear-headed in battle. While we now know amethyst offers no protection against alcohol's effects, the belief persisted for centuries and gave us the gem's enduring name. The purple color of amethyst comes from iron. Specifically, it comes from trivalent iron in the Fe3+ oxidation state, substituting for silicon atoms in the quartz structure. But iron alone doesn't create the purple color. The crystal must also be exposed to natural radiation, typically from radioactive elements in the surrounding rocks. This radiation creates what are called color centers in the crystal lattice, and these color centers absorb specific wavelengths of light, producing the purple hue we see. The finest amethyst traditionally came from Russia, particularly from the Ural Mountains, and this Siberian amethyst set the standard for color, deep purple with red or blue flashes. However, massive deposits discovered in Brazil in the Paraná Basin transformed the amethyst market. Today, Brazil produces most of the world's amethyst, with Uruguay and Zambia as other major sources. Zambia produces approximately 1,000 tons of amethyst annually from deposits that create intense purple stones, though often in smaller crystals than Brazil. Amethyst forms in geodes, hollow rocks lined with crystals, and in veins within volcanic rocks. When mineral-rich fluids move through these spaces and slowly cool or evaporate, crystals grow from the walls inward. The amount of iron in solution and the intensity of radiation exposure determine how deep the purple color becomes. Some amethyst is so pale it's nearly colorless, while the finest specimens achieve that deep, saturated purple that commands premium prices in jewelry. But amethyst holds another secret. Heat it, and it changes color. When amethyst is heated to between 350 and 450 degrees Celsius, iron impurities oxidize, and the purple transforms into yellow or orange. This heat-treated amethyst is sold as citrine. And here's a fact that surprises most people. Almost all citrine on the market today is actually heated amethyst. Natural citrine is exceptionally rare. True natural citrine forms when quartz crystals grow in environments where aluminum creates color centers instead of iron. The resulting yellow to orange color is genuine, unheated, and valuable precisely because of its rarity. Natural citrine tends to be paler than heat-treated material, often a soft golden yellow rather than the bright orange that heat treatment produces. Historically, citrine was often confused with topaz and sold as gold topaz or Spanish topaz, though it's a completely different mineral from true topaz. Here's where it gets interesting from a gemological perspective. You can often tell heat treated from natural citrine by looking carefully at the color distribution. Natural citrine usually has gentle, even color or subtle zoning that follows the crystal's growth patterns. Heat-treated amethyst often shows color concentrated near fractures, or shows an unusual reddish tint that natural citrine lacks. Under a microscope, the two can reveal different internal features, though this requires expertise to interpret. Now let's turn to rose quartz, and this is where our understanding of quartz changed dramatically just a couple of decades ago. For years, scientists believed rose quartz got its pink color from trace amounts of titanium, manganese, or iron. The color seemed to be evenly distributed through the material, and it was known that rose quartz would fade if exposed to strong sunlight for extended periods, then recover its color in darkness. Then, in 2001, researchers at Caltech made a discovery that rewrote the books. By dissolving rose quartz in hydrofluoric acid, one of the few substances that attacks quartz, they recovered tiny fibrous inclusions, finer than human hair. These microscopic fibers themselves were pink, and they made up only about 0.05 to 0.15% of the stone's mass. Chemical analysis revealed these fibers were a mineral related to dumortierite, a boron-containing aluminum silicate. This discovery explained several mysteries about rose quartz. It explained why rose quartz almost never forms distinct, well-shaped crystals, like amethyst or clear quartz. The tiny inclusions disrupt orderly crystal growth, so rose quartz typically occurs in massive chunks rather than crystal points. It explained the six-rayed star effect, asterism, that appears when rose quartz is cut as a cabochon and viewed under a single light source. The stars are caused by light reflecting off the aligned fibrous inclusions. Rose quartz is found worldwide, with major deposits in Brazil, Madagascar, India, and the United States. The softly glowing pink color makes it popular for decorative carvings and jewelry. Unlike some color in quartz, which can be intense and saturated, rose quartz tends toward gentle, milky pinks that diffuse light softly. Some rose quartz is so pale it's nearly white, while the finest specimens achieve a strong pink that remains translucent. Smoky quartz takes us back to radiation-induced color centers, but with a different mechanism than amethyst. Smoky quartz ranges from light gray-brown to nearly black, and this color forms when natural radiation affects aluminum impurities in the crystal. The radiation creates holes in the electron structure around aluminum ions, and these defects absorb light to create the smoky color. Very dark smoky quartz has special names. Nearly opaque black smoky quartz is called morion. Smoky quartz from Scotland's Cairngorm Mountains was traditionally called Cairngorm, and it became Scotland's national gemstone. Scottish jewellers set Cairngorm in traditional Scottish jewellery designs, particularly in sciandubas, the ceremonial daggers worn with Highland dress. The intensity of smoky colour depends on two factors: the amount of aluminum in the quartz and the radiation dose it received. Some smoky quartz from areas with high natural radioactivity is so dark it's almost completely opaque. Collectors prize these dark specimens, while jewelers often prefer lighter material that shows more transparency. Interestingly, smoky quartz is one variety where heat treatment can remove color rather than enhance it. Heating smoky quartz will often drive off the color, leaving clear quartz. Let's talk about milky quartz, because it's actually the most common variety of quartz on Earth, even though it doesn't get as much attention as the colored varieties. Milky quartz is white and opaque, caused by countless tiny fluid inclusions. microscopic cavities filled with water or carbon dioxide. These inclusions scatter light, making the quartz look white and cloudy rather than transparent. Milky quartz is the common vein quartz that geologists find in rock outcrops worldwide. It forms in fractures and veins in many types of rock, crystallizing from hydrothermal fluids moving through the Earth's crust. While it might not be as eye-catching as amethyst or smoky quartz, milky quartz played a crucial role in gold mining history. Gold often occurs in milky quartz veins, and prospectors learned to recognize these white outcrops as signs of potentially gold-bearing rock. The 49ers rushing to California looked for quartz veins that might contain gold, and milky quartz led them to some of the richest strikes. Rutilated quartz deserves special mention because of its unique appearance. This variety contains needle-like inclusions of rutile, titanium dioxide crystals that formed inside the quartz. These golden, reddish, or black needles can be sparse or so dense they create a spectacular internal landscape. The needles are sometimes called Venus hair or angel hair, and they can be straight, curved, or arranged in star patterns. When skilled lapidaries cut rutilated quartz, they orient the cut to best display the needle patterns. Large pieces can be carved into spheres or eggs, where light passes through from all angles to illuminate the internal structure. Some rutilated quartz contains needles arranged in three-directional star patterns. When cabochon cut with the star oriented correctly, these pieces show spectacular asterism. Tiger's eye is another inclusion variety with a fascinating story. For more than a century, mineralogists believed tiger's eye formed through a process called pseudomorphosis, where quartz slowly replaces chrysallite, a blue asbestos mineral, fiber by fiber, preserving the fibrous structure. The golden-brown chatoyancy, the cat's eye effect, was thought to come from this replacement process, with iron oxide coating the fibers. But research in 2003 revealed a more complex story. Mineralogists Heaney and Fisher demonstrated that tiger's eye doesn't form through simple replacement. Instead, quartz and chrysallite fibers grow simultaneously through what's called a crack seal mechanism. Parallel cracks open in the host rock. Quartz and chrysallite fill them. The cracks seal shut. New cracks form parallel to the first, and the process repeats. The result is layers of parallel fibers that diffract light to create that wonderful chatoyant shimmer. The golden brown color in tiger's eye comes from goethite, an iron oxide hydroxide that coats the fibers. Before iron oxidation, the material is blue and called hawk's eye. If you heat tiger's eye, it can turn reddish. This is sold as red tiger's eye, or sometimes ox eye. Natural red varieties do exist, but are less common. Before abundant deposits were discovered in South Africa in the 1870s, tiger's eye was rare enough to sell for extraordinary prices, half an ounce of gold per carat, making it more valuable than many precious gems. The South African deposits near Grickwitown transformed it into an affordable material, though fine, chatoyant specimens still command respect. Ametrine represents something unique, bicolor quartz, showing both purple amethyst and yellow citrine in distinct zones within a single crystal. For most of history, ametrine was so rare it was barely known outside of mineralogical circles. Then, in the 1900s, a remarkable source was discovered, the Anaheim mine in eastern Bolivia. Legend says Spanish conquistadors discovered the mine in the 1600s, but it was lost for centuries and rediscovered only in the 1960s. The mine remains the world's only significant commercial source of natural ametrine, producing crystals with dramatic purple and yellow color zones. The color zoning forms during crystal growth due to temperature differences in different parts of the growing crystal. One area experiences conditions that produce amethyst, while an adjacent area produces citrine, creating the distinctive bicolor pattern. Skilled gem cutters orient ametrine to show both colors dramatically, often with one color on each side of the gem or in geometric patterns. The rarity of natural ametrine makes it sought after by collectors, though some ametrine on the market is created by partially heat-treating amethyst. Now we shift from macrocrystalline quartz, varieties where individual crystals can be seen, to cryptocrystalline or microcrystalline quartz, where the crystals are so tiny they can only be resolved under high magnification. These varieties have their own rich history and distinctive properties. Chalcedony is the general term for cryptocrystalline quartz. But here's something most people don't know. Chalcedony isn't pure quartz. It contains a mixture of quartz and a related silica mineral called moganite, with moganite making up anywhere from 1 to 20% of the material. Over geological time, moganite slowly converts to quartz, so very ancient chalcedony contains less moganite than recently formed material. The microscopic crystals in chalcedony are arranged in fibrous bundles, rather than the blocky crystals of macrocrystalline quartz. This structure gives chalcedony different properties. It's somewhat more porous, takes dye more readily, and has a waxy luster rather than the glassy luster of crystalline quartz. Pure chalcedony, without distinctive patterning or coloring, ranges from white to grey to blue. The blue tones are particularly interesting because they result from Rayleigh scattering, the same phenomenon that makes the sky blue. Tiny structural variations scatter shorter blue wavelengths of light, more than longer wavelengths, creating a gentle blue glow in the finest specimens. Agate takes chalcedony and adds something special: bands. Agate forms in cavities in volcanic rock, typically when silica-rich solutions deposit successive layers over long periods. Each layer may differ slightly in composition, crystal size, or impurity content, creating visible bands when the agate is cut and polished. These bands can be straight, curved, circular, or wildly irregular, depending on how the cavity filled. The distinction between agate and jasper comes down to transparency. Agate is translucent, meaning light passes through it, while jasper is opaque. This seems simple, but it's based on real physical differences. Agate's relatively pure silica allows light transmission, while jasper contains up to 20% non-silica impurities, clay minerals, iron oxides, and other materials that block light. Jasper comes in an astounding array of colors and patterns. Red jasper, colored by iron oxide, is perhaps the most common, but jasper also occurs in yellow, brown, green, blue, and purple. Some jasper shows patterns called orbicular jasper, with circular structures, or picture jasper, where patterns suggest landscapes. Ancient peoples worldwide valued jasper for tools, weapons, and decorative objects, and it appears in archaeological sites from every inhabited continent. The famous bloodstone, or heliotrope, is actually a green jasper with red spots, traditionally believed to be drops of Christ's blood and therefore carried as a powerful talisman in medieval times. The green color comes from chlorite inclusions, while the red spots are iron oxide. Onyx is a banded agate with specifically black and white bands. True onyx shows these contrasting bands in parallel layers. Much material sold as onyx is actually dyed agate, because natural black and white onyx is less common than the market demands. The ancient Romans loved onyx for cameo carving, cutting through the white layer to reveal black beneath, or vice versa, creating dramatic two-tone relief carvings. Carnelian is a translucent, reddish-orange variety of chalcedony, colored by iron oxide. The name likely derives from the Latin word for flesh, or the cornel cherry, whose berries share carnelian's color. Ancient Egyptians used carnelian extensively in jewelry and amulets. Some of the oldest known carved beads are carnelian, dating back thousands of years. The warm color and relatively easy workability made carnelian popular worldwide, from ancient Mesopotamia to the Indus Valley civilization to Bronze Age Europe. Chrysoprase represents chalcedony in its most valuable form, an apple green variety colored by nickel. Unlike most green gems, which owe their color to chromium or iron, chrysoprase gets its distinctive color from nickel oxide impurities, typically 1 to 3%. The finest chrysoprase comes from Australia's Queensland region, particularly the Marlborough district, where nodules weighing up to 1,470 kilograms have been found. The word chrysoprase means gold leek in Greek, referring to its color. Ancient Greeks and Romans prized it, and it experienced a revival in Europe in the 14th century, when deposits were discovered in Silesia. The green color can fade in sunlight, but can be restored by storing the stone in damp conditions, suggesting the color is at least partly related to water content. Now we come to flint and chert, which deserve special attention because of their historical importance. These crypto-crystalline varieties of quartz, often with slightly different mineral composition but similar properties, shaped human history more than perhaps any other materials. Flint typically refers to the dark grey to black nodular form found in chalk and limestone formations, while chert is a more general term for similar material in other rock types. Both have essentially identical properties. They're hard, 7 on the Mohs scale, and they fracture conchoidally, meaning they can be broken to produce incredibly sharp edges. The Stone Age wasn't just a poetic term. It describes a period spanning more than 2.5 million years, when stone tools, primarily made from flint, chert, and other forms of quartz, were humanity's primary technology. The oldest known stone tools date to at least 2.6 million years ago. These older one tools from East Africa are often made from quartz or quartzite, but tool making evolved dramatically. By 1.76 million years ago, early humans were creating Acheulean hand axes, teardrop-shaped tools that required significant skill and planning to manufacture. These weren't rough cobbles randomly smashed. They were carefully crafted, showing that our ancestors understood flint's properties with remarkable sophistication. Research at Deep Kloof rock shelter in South Africa revealed that around 71,000 years ago, inhabitants of the Still Bay culture deliberately selected quartzite for spear tips because it combined two seemingly contradictory properties. When making the fine edges, the stone fractured easily, but when force was applied lengthwise, as happens when a spear strikes prey, the stone was extremely strong. This represented sophisticated materials science. Even more fascinating is evidence from Lesotho, showing that around 14,000 years ago, people suddenly began making tiny crystal quartz tools less than 1 centimeter long. They had more practical materials available like chert, but they chose crystal quartz possibly for symbolic reasons. Crystal quartz produces sparks when struck, and based on what we know about the importance of quartz in later southern African cultures, these ancient communities may have believed they could harness the crystal's power in some way. Flint quarrying became one of humanity's earliest industrial enterprises. At Grimes Graves in England, Neolithic people dug nearly 400 mine shafts, some more than 12 meters deep, to extract high-quality flint layers from around 4,000 years ago. This wasn't casual gathering. It was organized mining, that required planning, labor coordination, and presumably trade networks to distribute the finished products. The importance of flint continued long after the Stone Age ended. For thousands of years, flint remained essential for fire starting. Striking flint against steel produces sparks hot enough to ignite tinder, a technology that persisted until matches became widely available in the 19th century. Flint was used in firearms from the flintlock era, 16th to 19th centuries, where a piece of flint striking steel created the spark that ignited gunpowder. Architectural applications persisted into modern times. Throughout England and Northern Europe, flint nodules were used as building stones, creating distinctive buildings with walls of black flint set in lighter mortar. Medieval churches, manor houses, and even humble cottages were built with flint, a practice continuing into the 19th and even 20th centuries in some areas. The crypto-crystalline varieties of quartz share certain properties that distinguish them from their macrocrystalline cousins. They're slightly more porous, making them more susceptible to dye treatments. They have a waxy luster rather than glassy. They tend to be tougher, more resistant to breaking, even though they're the same hardness, because the tiny interlocking crystals resist fracture propagation. This toughness made jasper, agate, and flint ideal for ancient tool use and decorative carving. Understanding the distinction between macrocrystalline and cryptocrystalline quartz helps explain why ancient peoples sometimes chose one variety over another for specific purposes. Large, clear crystals were valued for their beauty and perceived spiritual properties. Chalcedony varieties could be carved with fine detail that would fracture out in coarser material. Flint's predictable fracture and extreme sharpness made it ideal for tools and weapons. Each variety had its purposes, and each tells us something about the people who valued it. The formation of quartz crystals is a story written in temperature, pressure, time, and chemistry. Unlike minerals that form almost instantly, such as the flash of fulgurite when lightning strikes sand, quartz crystals typically grow slowly, atom by atom, in environments that human timescales can barely comprehend. There are 4 main geological processes that create quartz, each producing crystals with distinctive characteristics. Let's explore each in turn. Hydrothermal formation represents the most common way large, well-formed quartz crystals develop. Picture this. Deep in Earth's crust, water heated to temperatures between 250 and 450 degrees Celsius circulates through fractures in rock. At these temperatures and pressures, water can dissolve significant amounts of silica that would be insoluble at surface conditions. This superheated silica-rich fluid is called a hydrothermal solution. As this hot fluid moves through fractures and cavities in the rock, it begins to cool or experiences changes in pressure or chemical conditions. When this happens, the solution can no longer hold as much dissolved silica, so silicon dioxide begins to crystallize out. The crystals grow slowly, layer by layer, with silicon and oxygen atoms finding their proper places in the growing lattice. The key word here is slowly. Laboratory experiments have measured hydrothermal crystal growth, and under ideal conditions, quartz can grow about 0.4 to 1 millimeter per day along the Z direction, the direction perpendicular to the crystal's long axis. This might not sound slow, but remember that crystals forming in nature rarely experience ideal conditions consistently. Growth rates fluctuate with changes in temperature, pressure, and solution chemistry. A crystal might grow relatively quickly for a period, then growth might nearly stop, then resume. The history of these changing conditions is sometimes recorded in growth zones visible within the crystal. A remarkable study published in Nature Communications in 2020 revealed that in certain pegmatite environments, quartz crystals can experience episodes of extraordinarily rapid growth. Under specific conditions, growth rates can accelerate from 10 to the minus 6 meters per second to 10 to the minus 5, or even 10 to the minus 4 meters per second. At these speeds, meter-sized crystals could theoretically form within days rather than millions of years. This finding challenged previous assumptions about crystal growth timescales and suggests that episodic rapid growth may be more common than previously thought. Geodes offer a perfect window into hydrothermal quartz formation. These hollow rocks, lined inside with crystals pointing inward, form when silica-rich fluids percolate through gas bubbles trapped in cooling lava, or when fluids fill cavities in sedimentary rock. Over thousands of years, crystals grow from the walls inward, creating those stunning, crystal-lined interiors that fascinate mineral collectors. The largest geodes can be big enough to walk inside. Cathedral geodes from Uruguay can be several meters tall. Igneous formation of quartz happens when silica-rich magma cools. Magma is molten rock, and when it contains high proportions of silicon dioxide relative to magnesium and iron, it's called felsic or silicic magma. Granite forms from felsic magma that cools slowly underground, and quartz is one of granite's main constituents, along with feldspar and mica. If you've ever looked closely at granite, you can identify the quartz by its glassy appearance and lack of cleavage. Pegmatites represent a special case of igneous formation. These extremely coarse-grained rocks form from the last remaining fluids after most magma has crystallized. These residual fluids are enriched in elements that don't easily fit into common minerals, and they can be rich in dissolved water and other volatiles. When pegmatites crystallize, conditions favor the growth of enormous crystals. Quartz crystals from pegmatites can be huge. Specimens weighing several tons are not uncommon in Brazilian pegmatites. The cooling rate matters enormously. If felsic magma erupts and cools quickly, quartz might form as tiny crystals in a rock called rhyolite. If the same magma cools slowly at depth, it becomes granite with larger crystals. If it forms a pegmatite, crystals can be gigantic. The chemistry is essentially the same, but the cooling rate determines crystal size. Metamorphic quartz forms when existing rocks are subjected to heat and pressure deep in Earth's crust. When sandstone, which is already mostly quartz grains, experiences metamorphism, the individual grains grow and fuse together, forming quartzite. Under intense heat and pressure, the boundaries between grains disappear as quartz recrystallizes, creating a rock that's nearly pure quartz, harder and more durable than the original sandstone. This process doesn't add quartz. It reorganizes existing quartz into a denser, more interlocked structure. Quartzite is so hard and tough that it resists weathering extremely well. The Baraboo quartzite in Wisconsin, formed from ancient beach sand about 1.7 billion years ago, creates ridges that still stand high today because the quartzite erodes so much more slowly than surrounding rocks. Sedimentary processes produce a different kind of quartz occurrence. As mountains erode, quartz grains weather out and accumulate in rivers, beaches, and sand dunes. Because quartz is so resistant to chemical weathering and so hard, it outlasts most other minerals. Feldspar, for instance, weathers to clay. Mafic minerals break down to iron oxides, but quartz grains persist, accumulating in sediments that become sandstone. Pure quartz sandstone, with 95% or more quartz content, is called orthoquartzite. These rocks form in environments where sediments have been weathered and transported so extensively that nearly everything except quartz has been removed. Ancient beaches and shallow seas produced extensive orthoquartzite formations. When these sedimentary quartz sandstones metamorphose, they become the quartzites we discussed earlier. Alpine quartz crystals tell a particularly dramatic story of formation. These crystals, found in fractures in high mountains like the Alps, formed at tremendous depths, 20 to 50 kilometers down, where temperatures reached 200 to over 1,000 degrees Celsius. They grew in fractures in metamorphic rocks, crystallizing from hydrothermal fluids circulating at these depths. Over millions of years, tectonic forces lifted these rocks toward the surface, and erosion exposed the crystal-bearing veins. The uplift and erosion continue today. Every year, erosion exposes quartz crystals in the Alps that have never seen daylight before. Alpine crystal hunters, a profession with traditions going back centuries, search for these freshly exposed pockets, sometimes finding spectacular specimens. These traditional crystal hunters, called Strahler, in German-speaking Alpine regions, combine mountaineering skills with geological knowledge. They study rock formations, recognize subtle signs of crystal-bearing veins, and sometimes work in dangerous conditions at high altitudes to extract perfect specimens. The finest alpine crystals can command prices of thousands of dollars from collectors who value their clarity, crystal form, and provenance from these legendary deposits. The voids where alpine crystals form, called vugs or pockets, can range from fist-sized cavities to chambers large enough for a person to crawl inside. When a Strahler breaks into a previously sealed pocket, they might find crystals that formed tens of millions of years ago, pristine and undisturbed, their faces gleaming as if they grew yesterday. The moment of discovery, opening a crack in the rock to reveal sparkling crystal points, represents the culmination of knowledge, effort, and often considerable luck. Now let's talk about synthetic quartz, because the ability to grow quartz in the laboratory revolutionized the electronics industry. In the 1930s and 40s, German mineralogist Richard Nacken pioneered hydrothermal quartz synthesis. The process mimics nature, but greatly accelerates it. A large steel pressure vessel, called an autoclave, is partially filled with a sodium hydroxide or sodium carbonate solution. Natural quartz, nutrient, crushed quartz fragments, is placed at the bottom, while seed crystals are suspended above. The autoclave is heated, so the bottom is hotter than the top. The hot solution at the bottom dissolves quartz. The silica-rich solution rises by convection, and when it reaches the cooler upper zone, it becomes supersaturated and deposits quartz on the seed crystals. Under these optimized conditions, synthetic quartz grows at rates of about 0.4 to 1 millimeter per day in the Z direction, far faster than most natural crystal growth. Within weeks, crystals large enough for industrial use are produced. By the 1950s, Bell Laboratories and other companies were growing synthetic quartz commercially. And by the 1970s, virtually all quartz used in electronics was synthetic. Synthetic quartz is not fake quartz. It has exactly the same composition and structure as natural quartz, just grown in weeks rather than millennia. In fact, synthetic quartz is often superior for technical applications, because the growth conditions can be precisely controlled, producing crystals of exceptional purity and minimal defects. The formation, timescales of quartz vary enormously. Synthetic crystals grow in weeks. Under ideal natural hydrothermal conditions, crystals might achieve significant size in years to decades. More typically, natural crystals grow over thousands to millions of years. Some quartz crystals in ancient metamorphic rocks have resided in Earth's crust for billions of years. having formed, been buried, metamorphosed, and finally exposed at the surface through the slow but relentless processes of geology. Understanding quartz formation helps us appreciate each crystal as a frozen record of geological processes. Every crystal tells a story of the temperature and pressure at which it formed, of the chemical composition of the fluids from which it grew, of the time it took to achieve its size, and of the journey from its birthplace deep in the earth to wherever we find it today. The relationship between humans and quartz stretches back further than almost any other material. To understand this relationship is to trace the development of human culture itself. The oldest evidence of stone tool-making comes from Gona, Ethiopia, where tools dated to about 2.6 million years ago have been found. These Oldowan tools, named after Olduvai Gorge, where similar tools were first extensively studied, represent the dawn of human technology. Our ancestors selected specific stones, including quartz and quartzite, for their properties. They understood, on some level, that striking these stones in particular ways would produce flakes with sharp edges, suitable for cutting meat, processing plant materials, and working wood. This wasn't random behavior. Recent studies of stone tool manufacture show that creating even simple Oldowan tools requires understanding cause and effect, planning several steps ahead, and adjusting technique based on the stone's behavior. The choice of quartz and related materials was deliberate. These stones predictably produce useful flakes when struck properly. By 1.76 million years ago, toolmaking had evolved to produce Acheulean hand axes. These carefully shaped teardrop tools demonstrate remarkable skill and planning. Creating a well-made hand axe requires removing flakes in a specific sequence to thin and shape the stone, maintaining the right angles to prevent the piece from breaking, and often finishing with careful pressure flaking to create neat, regular edges. This technology persisted for over 1 million years, testament to its effectiveness. The sophistication of stone selection is revealed in research from Diepkloof rock shelter in South Africa, dating to about 71,000 years ago. Inhabitants chose quartzite specifically for spear points because its properties matched their needs perfectly. The stone flakes easily when creating the fine edges, but proves extremely strong when force is applied lengthwise through the spear point during hunting. This represents materials science, understanding different rocks, properties, and choosing the right one for the job. Even more intriguing is evidence from around 14,000 years ago in Lesotho, where people suddenly began making tiny crystal quartz tools, often less than 1 centimeter long. More practical materials were available, but they chose crystal quartz. The reason might be symbolic. When crystal quartz is struck, it produces flashes of light, triboluminescence. Based on what we understand about quartz's importance in later southern African cultures, this could suggest these ancient communities believed crystal quartz held special powers, possibly related to seeing the future or connecting with the spiritual realm. The choice of material went beyond mere function to incorporate meaning and belief. By 6,000 years ago, the Sumerians, who had invented writing and developed advanced urban civilization in Mesopotamia, were cutting and engraving quartz cylinder seals. These small cylindrical stones were carved with intricate designs in intaglio, cut into the surface. When rolled across soft clay, they left a raised impression identifying documents, goods, or property. Quartz's hardness made it ideal for this purpose. The seals wouldn't wear out from repeated use. Ancient Egypt's relationship with quartz spans the entirety of Egyptian civilization. From the pre-dynastic Badarian period around 4400 to 4000 BCE, Egyptians created quartz amulets for protection. They carved quartz into beads, pendants, and small figurines. Perhaps most dramatically, they embedded quartz crystals into statue eyes, creating an eerie, lifelike gaze that seems to follow the viewer. Egyptians also invented faience, a glazed ceramic material made from crushed quartz, mixed with small amounts of lime and plant ash, then fired. Faience could be molded into shapes and glazed in brilliant blue, green, or turquoise colors. It became the most popular material for mass-produced amulets. Millions of faience amulets were created, representing gods, protective symbols, and sacred animals. Some Egyptians were buried with quartz crystals placed on their foreheads, which was thought to provide safe passage to the afterlife. The ancient Greeks held fascinating beliefs about quartz. The Greek word krystallos, meaning ice, specifically referred to clear quartz, because Greek natural philosophers believed it was ice that had been so perfectly frozen by the gods that it would never melt. The philosopher Theophrastus wrote about this belief, noting that the finest crystal came from the coldest mountains, near glaciers, evidence to the Greeks of its frozen origin. This belief persisted into Roman times. Pliny the Elder, writing in the 1st century CE in his massive natural history encyclopedia, documented the Roman fascination with rock crystal. He noted that crystal was found near alpine glaciers, confirming the frozen water theory. Romans carved large spheres of crystal and held them in summer to cool their hands. Physicians used crystal balls exposed to sunlight as healing tools, possibly recognizing that quartz transmits light particularly well. Wealthy Romans paid astronomical prices for fine crystal objects. One Roman woman reportedly paid 150,000 sesterces for a single crystal ladle, an amount equivalent to about 50,000 measures of grain, representing an enormous fortune. Crystal drinking vessels, decorative objects, and jewelry pieces commanded premium prices. The Romans also used crystal balls, crystallum orbis, in divination, with soothsayers claiming to see the future in the transparent depths. In China, the story of quartz stretches back over 7,000 years. Jade production began around 5000 BCE, and quartz played an essential supporting role. Jade has a hardness of 6.5 to 7 on the Mohs scale, making it difficult to carve. Quartz, with its hardness of 7 and abundance, served as the abrasive of choice for shaping jade. Craftsmen used quartz sand and water, rubbing patiently for hours or days to slowly grind jade into desired forms. But quartz had its own value in China. Clear quartz was called water jade, or water crystal, and was believed to be water that had frozen for thousands of years and would never thaw. The same belief as the Greeks, arising independently. The Chinese considered colorless quartz the elite among stones, embodying purity and perfection. Prince Liu Sheng, who died in 113 BCE, was buried in one of the most elaborate burial suits ever created, a suit made of 2,498 pieces of jade, stitched together with gold thread. Each piece had to be carefully shaped and polished, work that would have required vast amounts of quartz abrasive and thousands of hours of labor. Japanese mythology gave quartz a different symbolic meaning. Clear quartz crystal spheres represented the heart of a dragon, not Western dragons associated with destruction, but the wise, benevolent dragons of East Asian tradition. Dragons were associated with power, wisdom, water, and good fortune. A crystal ball embodied the dragon's essence. Temple carvings throughout Japan depict dragons clutching crystal spheres. According to Japanese tradition, smaller rock crystals were the congealed breath of the white dragon, while larger specimens were the saliva of the violet dragon. The Museum of Fine Arts in Boston holds an exceptional crystal sphere, 11.3 inches in diameter, that was discovered at Japan's Ontake Mountain in 1876. Such spheres required enormous skill to create, as any flaw or fracture would cause the ball to shatter during grinding and polishing. Cherokee Native American mythology describes the Ulunsuti, a sacred crystal from the forehead of the Uktena, a giant horned serpent. According to tradition, possessing the Ulunsuti brought success in hunting, love, rainmaking, and prophecy. The crystal showed the future, with events appearing in its clear depths as a tree is reflected in a still stream. Cherokee families kept personal crystals wrapped in deerskin and hidden. When someone died, their crystal passed to the next generation and was believed to maintain communication with the deceased's spirit. In Australian Aboriginal spirituality, quartz is the most common material identified as marbon, a mystical substance believed to grant medicine men their powers. During initiation rituals, quartz crystals were spiritually inserted into initiates' bodies, granting them abilities like X-ray vision and healing power. While the insertion was metaphorical rather than literal, the belief in quartz's spiritual potency was absolutely real and central to Aboriginal understanding of spiritual power. Greek mythology explained rose quartz's color through the story of Aphrodite and Adonis. When the beautiful Adonis was attacked by a boar, Aphrodite rushed to save him, cutting herself on thorns in her haste. Their blood mingled and stained white quartz pink forever, creating rose quartz as an eternal symbol of their love. The Passage Tomb at Newgrange in Ireland, built around 3200 BCE, older than Stonehenge and the Egyptian pyramids, features a striking facade of white quartz stones. These stones were transported from the Wicklow Mountains many miles away, suggesting they held special significance. The tomb's alignment with the winter solstice sunrise creates a dramatic illumination effect, and the white quartz facade would have made the monument even more spectacular, glowing in the low winter sun. In Hinduism, quartz crystal, called sphatic or spatica, has been used for prayer beads for centuries. Traditional malas contain 108 beads, plus a guru bead. Sphatic malas are associated with the planet Venus in Vedic astrology and are valued for their supposed cooling properties during meditation. In Buddhism, rock crystal is listed as one of the 7 precious substances, materials of great spiritual value. Throughout Europe in the medieval period, crystal balls became associated with divination and magic. The sceptre of Scotland features a crystal ball in its finial, possibly honouring Druid traditions. In 1582, John Dee, mathematician, astronomer, and advisor to Queen Elizabeth I, claimed an angel named Uriel gave him a magic crystal for communicating with angels. This crystal is now in London's Science Museum, a tangible link to Renaissance mysticism. Crystal balls required exceptional skill to create. The Smithsonian Institution houses a 12.75-inch diameter, 107-pound sphere of flawless Burmese rock crystal, the largest fine crystal ball in any museum collection. Creating such a sphere without modern tools would have required months or years of patient grinding and polishing, constantly checking the sphere's roundness and transparency. What all these cultures shared was a recognition that quartz was special, different from ordinary stones. Its clarity, its hardness, its ability to take a fine polish, its resistance to weathering, even its tribioluminescence and piezoelectric properties, though these weren't understood scientifically. All these qualities marked quartz as extraordinary. Different cultures interpreted this specialness through their own spiritual and philosophical frameworks. But the common thread is clear. Quartz mattered to humans in ways that went far beyond mere utility. In 1880, two brothers working in Paris would make a discovery that would eventually revolutionize technology. Pierre Curie, age 21, and Jacques Curie, age 25, were conducting experiments with crystals at the Faculty of Sciences of Paris under the direction of Charles Friedel. They were investigating piezoelectricity, the production of electrical charges in certain crystals when heated. But their experiments led them to something even more remarkable. The Curie brothers discovered that certain crystals, including quartz, tourmaline, and Rochelle salt, generated electrical charges when subjected to mechanical pressure. They called this the piezoelectric effect, from the Greek piezo, meaning to squeeze or press. The remarkable thing is that they made this discovery using very simple equipment: tinfoil, glue, wire, magnets, and a jeweler's saw. Their experimental elegance and precise measurements demonstrated that when you compressed quartz crystals along certain axes, electrical charges appeared on the crystal surfaces proportional to the applied pressure. The magnitude of this effect is astonishing. A 1 centimeter cube of quartz, subjected to 2 kilonewtons of correctly applied force, about 500 pounds of force, can generate 12,500 volts. This is not a lot of current, but the voltage is impressive, and the effect is perfectly reversible. The following year, in 1881, Gabriel Lippmann approached the problem theoretically. Using fundamental thermodynamic principles, he predicted that if the direct piezoelectric effect existed, mechanical stress creating electrical charges, then the converse effect must also exist. Applying an electrical field to these crystals should cause mechanical deformation. The Curie brothers immediately tested this prediction and confirmed it was correct. This reversibility is crucial. A quartz crystal will generate voltage when compressed, but if you apply voltage to the same crystal, it will physically deform. This bidirectional property is what makes quartz oscillators possible. Apply an alternating voltage to a quartz crystal, and it will vibrate mechanically at a precise frequency determined by the crystal's dimensions and cut. The vibrating crystal generates an electrical signal at the same frequency. This signal can be electronically amplified and fed back to sustain the vibration. The result is an oscillator of extraordinary stability and precision. For about 30 years after its discovery, piezoelectricity remained mostly a laboratory curiosity. Scientists explored which crystals exhibited the effect and worked to understand the crystallographic principles involved. In 1910, Waldemar Voigt published his comprehensive textbook on crystal physics, which rigorously described the 20 natural crystal classes capable of piezoelectricity and defined the piezoelectric constants using tensor analysis. The first practical application came during World War I. Paul Langevin in France developed an ultrasonic submarine detector using thin quartz crystals glued between two steel plates. When the quartz was electrically excited, it generated ultrasound waves that traveled through water. When reflections returned from a submarine, the quartz converted the mechanical waves back to electrical signals that could be detected. This was sonar, sound navigation, and ranging, and it represented the first major practical use of piezoelectricity. World War II created enormous demand for quartz crystals. Crystal-controlled oscillators were essential for radio communications, allowing different units to maintain precise frequencies without interfering with each other. Before the war, only about 100,000 crystal units were produced in the United States in 1939. The war created such desperate demand that quartz crystal oscillator development became the second largest scientific undertaking in the United States after the Manhattan Project. Brazil was virtually the only source of suitable natural crystals, making quartz a strategic material. Mining operations in Brazil expanded rapidly to meet wartime demand, with peak production reaching 2,411 metric tons in 1943. The supply situation was precarious enough that intensive efforts went into developing synthetic quartz production. Richard Nacken, in Germany, had pioneered hydrothermal quartz synthesis in the 1930s and 40s. After the war, companies, including Brush Development Company in the United States, scaled up production. By 1948, Brush was growing crystals 1.5 inches in diameter. Bell Laboratories developed commercial hydrothermal synthesis techniques by 1950, and within a few decades, virtually all quartz used in electronics was synthetic. In October 1927, Warren Marrison and J.W. Horton at Bell Telephone Laboratories built the world's first quartz clock. Their clock used a crystal oscillating at 50,000 Hz, with electronic frequency dividers creating usable timing pulses. Walter Guyton Caidi had invented the first quartz crystal oscillator in 1921, but Marrison and Horton created the first complete clock system. The development of quartz clocks revolutionized timekeeping. The best mechanical clocks might gain or lose 20 seconds per day. Early quartz clocks achieved accuracy better than 1,000th of a second per day, a 100-fold improvement. As technology advanced, quartz clocks became smaller and more accurate. By the 1960s, precision quartz oscillators achieved stability better than 1 part in 10 billion. The key breakthrough for consumer applications came with the development of the quartz watch. The first wristwatch-sized quartz movement was incredibly difficult to develop. The oscillator, divider circuits, stepping motor, and battery all had to fit in a package small enough to wear, and the entire system had to run for at least a year on a tiny battery. On December 25, 1969, Seiko launched the Quartz Astron 35 SQ, the world's first commercially available quartz wristwatch. Only 100 pieces were produced initially, priced at 450,000 yen, equivalent to the cost of a small car. But the performance was revolutionary. Accuracy of plus or minus 0.2 seconds per day, or plus or minus 5 seconds per month. About 100 times more accurate than the best mechanical watches. The Astron achieved this accuracy using a crystal oscillating at 32,768 Hz. This specific frequency became the universal standard for quartz watches, and there's a beautiful reason why. 32,768 equals 2 to the 15th power. With a simple 15-stage binary counter, a chain of 15 flip-flops, each dividing the frequency by 2. This frequency can be divided down to exactly 1 Hz, providing 1-second pulses to drive the watch's hands or digital display. This choice of frequency balanced several factors. A lower frequency crystal would be physically larger and might not fit in a wristwatch. A higher frequency crystal would consume more power, reducing battery life. And 32,768 Hz is above the range of human hearing, so the crystal's vibrations are inaudible. The power of two relationship meant simple, efficient electronics could divide the frequency to 1 Hz, which is exactly what you need for accurate timekeeping. Standard quartz watches achieve accuracy of about 6 parts per million, gaining or losing approximately 15 seconds per 30 days. This is achieved with a crystal costing pennies and electronics simple enough to fit on a chip smaller than your fingernail. More sophisticated quartz watches with temperature compensation can achieve plus or minus 1 second per year, accuracy that would have seemed impossible before the quartz revolution. The introduction of affordable quartz watches created what's known as the quartz crisis in the Swiss watch industry. Between 1970 and 1988, Swiss watch industry employment collapsed from 90,000 to 28,000 workers, a loss of over 60,000 jobs. Swiss watch companies fell from 1,600 to 600 between 1970 and 1983. Mechanical watch exports fell from 40 million units in 1973 to only 3 million by 1983. Japanese companies, led by Seiko and Citizen, dominated the quartz watch market by sharing technology and manufacturing knowledge, rapidly overcoming technical challenges and creating new markets. Swiss manufacturers eventually adapted, but the transition was painful and fundamentally changed the industry. Mechanical watches increasingly became luxury items valued for craftsmanship rather than accuracy, while quartz watches dominated the mass market based on performance and affordability. Beyond timekeeping, piezoelectric quartz found countless applications. Quartz crystal oscillators became the timing references for virtually all digital electronics: computers, smartphones, network equipment, GPS systems. The internet itself depends on quartz oscillators, maintaining precise timing for data transmission. Medical ultrasound uses piezoelectric transducers, often made from quartz or other piezoelectric materials, to generate and detect ultrasound waves. These same waves that Langevin used to detect submarines now let doctors visualize fetal development, examine internal organs, and guide surgical procedures. High-intensity focused ultrasound can destroy kidney stones or tumors without surgery, all based on the piezoelectric effect. Quartz pressure sensors exploit piezoelectricity to measure pressure with extraordinary precision. These sensors can detect pressure changes as small as 0.01 psi, with measurements taking only 1 second. They're used in aerospace, industrial processes, oil and gas exploration, and scientific research. The piezoelectric effect in quartz is also used to generate sparks in gas lighters and stoves. When you press the ignition button, a spring-loaded hammer strikes a piezoelectric crystal, generating enough voltage to create a spark that ignites the gas. This simple, reliable ignition system has replaced pilot lights in millions of appliances. Looking back at Pierre and Jacques Curie's discovery in 1880, it's remarkable to consider that they were investigating what seemed like an obscure physical phenomenon: crystals generating electricity when squeezed. They could not have imagined that their discovery would become fundamental to modern technology, that billions of devices would depend on the effect they documented, or that the simple crystals they experimented with would become the timekeepers of civilization. The piezoelectric revolution demonstrates how fundamental scientific research, pursued for understanding rather than immediate application, can transform the world in ways impossible to predict. The Curie brothers weren't trying to invent watches or sonar or ultrasound. They were trying to understand how nature works. But by revealing a fundamental property of certain crystals, they opened doors to technologies that have become woven into the fabric of modern life. While piezoelectric applications represent quartz's most visible technological role, the mineral serves crucial functions across modern industry in ways most people never see or consider. Let's start with something fundamental: glass. Silica sand, which is primarily quartz, is the main ingredient in virtually all glass. For glass manufacturing, the sand must contain at least 95% SiO2 and less than 0.6% iron oxide, which would give glass an unwanted green tint. The sand is heated to temperatures reaching 1600 degrees Celsius, where it melts and combines with soda ash and limestone. The resulting mixture, when cooled, becomes glass. Every window you look through, every bottle you drink from, every light bulb illuminating your space, contains quartz transformed into glass. The global glass industry consumes millions of tons of silica sand annually. The specific properties of quartz, its high melting point, chemical stability, and optical clarity when pure, make it irreplaceable for glass production. But quartz's role in technology extends far beyond ordinary glass. Fused quartz, or fused silica, represents ultra-pure quartz melted and formed into special products. Unlike crystalline quartz with its regular atomic structure, fused quartz is amorphous. The atoms lack long-range order. This gives fused quartz unique properties. Fused silica transmits light from the ultraviolet through the visible spectrum and into the infrared. UV-grade synthetic fused silica transmits over 90% of light from 200 nanometers to 2 microns wavelength, with ultraviolet transmission extending down to 170 nanometers. Most glasses absorb UV radiation, but fused quartz's transparency to UV makes it essential for scientific instruments, UV sterilization equipment, and semiconductor photolithography. The semiconductor industry represents one of quartz's most critical modern applications. Virtually all telecommunications optical fibers worldwide are made from ultra-pure fused silica. The exceptional purity allows light signals to travel vast distances with minimal signal loss, enabling the global internet infrastructure. Without high-purity quartz, modern telecommunications would be impossible. High-purity quartz crucibles hold molten silicon at approximately 1425 degrees Celsius during the Czochralski process for growing single-crystal silicon ingots. These ingots are sliced into wafers that become the foundation for integrated circuits. The semiconductor industry accounts for approximately 50% of all high-purity quartz usage. The purity requirements are extreme. Semiconductor-grade quartz must contain less than 50 parts per million total impurities, with individual metal contaminants measured in parts per billion. A remarkable fact about the semiconductor industry's dependence on quartz: the spruce pine deposits in North Carolina, formed 380 million years ago, produce ultra-high purity quartz that supplies crucibles for much of global semiconductor manufacturing. This small region's geology makes it one of the few sources of quartz pure enough for the most demanding applications. The concentration of such critical resources in a single location has raised concerns about supply chain vulnerability. Hydraulic fracturing, fracking, represents an enormous industrial use of quartz sand. In this process, slurries of water, chemicals, and carefully graded quartz sand are pumped under extreme pressure into oil and gas wells, fracturing the rock and releasing trapped hydrocarbons. The sand grains prop the fractures open, allowing gas and oil to flow. The durability of quartz is essential. The sand must withstand crushing pressures without breaking down. Millions of tons of frac sand are used annually in oil and gas extraction. In construction and concrete, quartz sand plays essential roles. High-purity silica sand is used in manufacturing fiberglass, ceramics, and specialized concrete. The construction industry is one of the largest consumers of sand globally. And while not all construction sand is pure quartz, quartz typically comprises a significant fraction. Quartz serves as an abrasive in sandblasting, grinding wheels, and sandpaper. The hardness of 7 makes quartz effective for abrading softer materials, while being easier to work with than harder abrasives like corundum. Industrial sandblasting uses quartz sand to clean metal surfaces, remove paint, and prepare surfaces for coating. Though safety regulations have restricted some applications due to silicosis risks from inhaling fine quartz dust. The foundry industry uses quartz sand in metal casting. Sand molds for casting metal must withstand high temperatures without breaking down or reacting with the molten metal. Quartz's high melting point and chemical stability make it ideal. Foundries consume vast quantities of specially graded quartz sand for creating the molds into which molten metal is poured. Precision optics depend on quartz in multiple ways. High-quality fused silica is used for telescope mirrors, camera lenses, and scientific instruments. Its low thermal expansion means optical elements maintain their shape and focus despite temperature changes. Space telescopes, like Hubble, use fused silica optics that must maintain nanometer-scale precision across extreme temperature variations. The quartz market has grown into a multi-billion-dollar global industry. The overall quartz market was valued at approximately $8 billion in 2024 and is projected to reach $12.5 billion by 2033. The high-purity quartz market specifically was valued at approximately $894.6 million in 2022 and is expected to reach $1.5 billion by 2031. Global natural quartz production reached approximately 422 million tons in 2024. Brazil dominates production with estimated reserves of about 53 million metric tons, representing approximately 95% of known world supply. Other significant producers include the United States, particularly the spruce pine deposits, and various Asian and European sources. The pricing of quartz varies enormously depending on purity and application. Ordinary quartz sand for construction might sell for dollars per ton. High-purity quartz for semiconductor applications commands prices around $10,000 per ton or more. Single crystal synthetic quartz for specific electronic applications can be even more valuable. Gem quality quartz varieties vary from inexpensive amethyst selling for a few dollars per kilogram to rare natural citrine or fine chrysoprase, fetching hundreds of dollars per kilogram. Quartz halogen lamps use fused quartz envelopes that can withstand the high temperatures generated by the halogen cycle. The quartz envelope must transmit light efficiently while containing the hot halogen gas that extends bulb life. These lamps provide bright, white light and are used in automotive headlights, stage lighting, and industrial applications. In water purification, UV transparent quartz tubes house the UV lamps that sterilize water by destroying bacterial DNA. The quartz must transmit UVC radiation at 254 nanometers while protecting the lamp from water. Municipal water treatment facilities processing millions of gallons daily. Aquarium sterilization systems maintaining delicate marine ecosystems, and point-of-use water purifiers protecting individual households all rely on quartz's UV transmission properties. The quartz tubes must maintain their transparency over thousands of hours of operation while withstanding thermal cycling as the lamps heat and cool. High-purity fused quartz tubes meet these demanding requirements, with specialized grades developed specifically for UV sterilization applications. The global market for UV water treatment systems continues expanding. as water scarcity and contamination concerns grow, creating increasing demand for high-quality quartz components. Laboratory glassware increasingly uses fused quartz for applications requiring chemical inertness, thermal stability, or UV transmission. Quartz cuvettes for spectroscopy allow UV and visible light analysis. Quartz tubes for high-temperature reactions withstand thermal cycling that would shatter regular glass. The electronics industry's dependence on quartz extends beyond oscillators and semiconductors. Quartz is used in fiber optic components, electro-optical devices, and specialized sensors. The combination of piezoelectric, optical, and thermal properties makes quartz uniquely versatile for electronic applications. Looking at quartz's role across modern industry reveals how a single mineral supports multiple critical technologies. From the fiber optic cables carrying internet data to the watches marking our time, from the glass in our windows to the crucibles growing silicon for our computers, quartz touches nearly every aspect of modern technological life. The same mineral our ancestors shaped into tools millions of years ago now enables the digital age, a testament to quartz's extraordinary range of useful properties and humanity's increasing sophistication in exploiting those properties. Throughout history, extraordinary quartz specimens have captivated collectors, scientists, and the general public. These exceptional crystals push the boundaries of size, clarity, color, or geological significance, and each tells a story worth exploring. The world's largest single quartz crystal was discovered near Itapora in Goiás, Brazil. This enormous crystal measured approximately 6.1 meters long by 1.5 meters wide by 1.5 meters tall. That's about 20 feet by 5 feet by 5 feet. It weighed over 39,900 kilograms, or roughly 88,000 pounds, about 44 tons. Moving such a massive specimen would require industrial equipment, and finding a buyer or museum capable of displaying it presents its own challenges. Even larger quartz crystal clusters have been found. The largest documented crystal cluster was unearthed in 1985 at the Otjua mine near Karibib, Namibia. This massive specimen weighed approximately 14,100 kilograms, over 14 tons, and measured about 3 meters wide by 3 meters high. The excavation from a 45-meter deep cave took 3 to 5 years to complete without damaging the specimen. Today, this remarkable cluster is displayed at the Crystal Gallery in Swakopmund, Namibia, where visitors can appreciate its sheer scale. In Brazil's pegmatite regions, individual quartz crystals weighing 40 metric tons have been documented, and crystals in the 1 to 5 ton range are considered relatively common in some deposits. The Minas Gerais, Goiás, and Bahia states produce exceptional specimens, with crystals large enough that mining them intact presents significant engineering challenges. Arkansas, which calls itself the quartz crystal capital of the world, has produced remarkable specimens for over a century. A quartz belt 30 to 40 miles wide runs through the Ouachita Mountains, and mining districts around Mount Ida have yielded countless fine crystals. The Burns quartz, discovered at the Coleman mine in 2016, weighs over 8,000 pounds and stands 7 feet tall. This spectacular cluster is now on permanent display at the Smithsonian Institution's National Museum of Natural History in Washington, D.C., where millions of visitors can see it. The Smithsonian's quartz collection includes other remarkable pieces. A 12.75-inch diameter, 107-pound perfect sphere of flawless Burmese rock crystal represents the largest fine crystal ball in any museum collection. Creating such a sphere would have required months or years of patient grinding and polishing, constantly checking for uniformity and maintaining clarity throughout the massive ball. Speaking of crystal balls, the Museum of Fine Arts in Boston holds an 11.3-inch diameter sphere discovered at Japan's Ontake Mountain in 1876. Japanese artisans created exceptional crystal balls through patient hand grinding, and large spheres of this quality were extremely rare and valuable. For clarity and perfection, the Herkimer diamonds from Herkimer County, New York, represent some of nature's most beautiful quartz crystals. These aren't actually diamonds, they're quartz, but they naturally form as double-terminated crystals pointed on both ends, with exceptional clarity and brilliant faces that need no polishing. The best Herkimer diamonds appear water clear, with sharp, lustrous faces, and often contain interesting inclusions like petroleum droplets or tiny crystals of other minerals. Amethyst geodes from Uruguay can achieve cathedral size, large enough to walk inside. These hollow geodes, lined completely with purple amethyst crystals, can be several meters tall and weigh multiple tons. They form in ancient lava flows where gas bubbles were slowly filled with amethyst depositing solutions over millions of years. When cut open and prepared for display, cathedral geodes create stunning natural chambers glittering with purple crystals. The Cullinan amethyst, a collection of extraordinary amethyst specimens from the Cullinan mine in South Africa, famous for the Cullinan diamond, includes crystals of exceptional size and color. Some individual crystals exceed 1 meter in length, with deep, saturated purple color throughout. For natural citrine, genuinely rare and valuable, some of the finest specimens come from Brazil's São Paulo and Bahia states, Russia's Ural Mountains, and France's Auvergne region. Natural citrine crystals exceeding several kilograms are extremely rare, and museum-quality specimens command premium prices from collectors. Rose quartz typically doesn't form distinct crystals, but occasional finds from Brazil, Madagascar, and Maine have produced recognizable crystal forms. These are exceptionally rare and valuable to collectors, specifically because well-formed rose quartz crystals are so unusual. For smoky quartz, Switzerland's Alps produced legendary specimens during the 19th and early 20th centuries, when professional crystal hunters would search alpine fissures for spectacular crystals. Some smoky quartz crystals from the Alps exceeded 0.5 meter in length, with deep, evenly distributed brown color. These specimens now reside in major European museums and command extraordinary prices when they appear at auction. The largest documented quartz crystals from pegmatites often achieve truly massive proportions. In addition to the Brazilian giants mentioned earlier, Madagascar has produced enormous quartz crystals from its extensive pegmatite fields. Some Malagasy crystals exceed 10 meters in length, though most of this length may be embedded in the surrounding rock, making extraction extremely difficult. Record-breaking faceted quartz gems demonstrate skilled lapidaries' ability to work with large, clean material. While large quartz crystals are relatively common compared to most gemstones, finding material clean enough to cut gems of hundreds or thousands of carats requires exceptional crystals. The largest faceted amethyst is reported to weigh over 10,000 carats, cut from a Brazilian crystal of unusual clarity and color. Rutilated quartz specimens with exceptional needle formations are highly prized by collectors. The best pieces show dense, aligned rutile needles, creating dramatic internal landscapes. Some specimens contain rutile, arranged in star patterns. When properly cut and oriented, these create spectacular asterism. Rutilated quartz gems exceeding 200 carats have been faceted from material with particularly attractive needle patterns. For tiger's eye, While the material is relatively common, cabochons exceeding 100 carats, showing strong, centered chatoyancy, are noteworthy. The largest tiger's eye cabochon, documented, weighs over 6,000 carats, though such large pieces may sacrifice chatoyancy quality for size. In terms of scientific significance, some quartz specimens carry value beyond their size or beauty. Quartz crystals that contain ancient water inclusions, called anhydrous quartz, preserve water that was trapped when the crystal formed. Some of these water inclusions are millions or even billions of years old, representing samples of ancient oceans or hydrothermal fluids. Phantom crystals, where growth stages are preserved as ghost-like outlines within clear quartz, record the crystal's growth history. Each phantom represents a pause in growth, when a thin layer of minerals was deposited on the crystal's surface before clear growth resumed. Some phantoms show multiple growth stages, creating a geological timeline frozen in crystal. The Jack Hills of Western Australia contain zircon crystals, the oldest terrestrial materials ever found at 4.4 billion years old, embedded in quartz-bearing sedimentary rocks. While the zircons, rather than the quartz, are the record holders, the quartz matrix helped preserve these ancient crystals that provide evidence of early Earth's conditions. Arkansas hosts an annual World Championship Quartz Crystal Dig, where participants can dig for their own quartz crystals at working mines. While finding museum-quality specimens is rare, the event maintains a tradition of recreational crystal hunting that goes back to when Arkansas crystal mining was a major industry. Collecting record-setting quartz specimens presents unique challenges. The largest crystals are essentially immovable without industrial equipment and can't realistically be privately owned or displayed. Even moderately large specimens weighing hundreds of kilograms require special display cases and structural support. Museums serve as the primary stewards of the most exceptional specimens, preserving them for scientific study and public education. The quest for exceptional quartz continues today. Each year, miners, collectors, and rockhounds discover new specimens that may set records or reveal new formation environments. The combination of quartz's abundance and the variability of its formation means that somewhere in Earth's crust, even more extraordinary crystals are waiting to be discovered. Quartz has accumulated more than its fair share of mysteries, myths, and misconceptions over the millennia. Some of these beliefs held for thousands of years before science revealed the truth. Others persist to this day, despite evidence to the contrary. Let's explore some of the most interesting examples. The crystal skull phenomenon represents one of the most persistent modern myths involving quartz. Around a dozen life-sized or near-life-sized crystal skulls exist in museums and private collections. For decades, these skulls were claimed to be pre-Columbian artifacts, created by ancient Mesoamerican civilizations like the Maya or Aztec. Stories proliferated about their mysterious origins, supposed mystical powers, and the advanced techniques required to create them. The truth, revealed through scientific analysis, is far less mysterious but historically interesting in its own right. Every examined crystal skull has been proven to be a 19th century creation, likely manufactured in Idar Oberstein, Germany, a center of quartz crafting using Brazilian quartz. The evidence is compelling and multifaceted. First, no crystal skull has ever been found in a documented archaeological excavation. Every single one either appeared in private collections with vague provenance or was purchased from dealers. Second, crystal skulls do not appear in any genuine Mesoamerican mythology, codices, or historical accounts. The ancient civilizations supposedly responsible for creating them never mentioned such objects. Third, and most damning, electron microscope analysis of the tool marks on the skulls revealed they could only have been made with modern rotary equipment. The microscopic scratches, cut patterns, and polishing marks are diagnostic of 19th and 20th century lapidary tools. Pre-Columbian peoples lacked this technology. They could carve quartz using stone tools and abrasives, but the resulting marks are distinctively different from those found on the crystal skulls. The source of most known skulls can be traced to Eugène Bobin, a French antiquities dealer operating in Mexico City between 1860 and 1880. He sold several crystal skulls during this period, claiming various origins for them. The British Museum purchased one from Tiffany & Co. in 1897 for £100 sterling. It's now catalogued as probably European 19th century AD. The Smithsonian skull arrived anonymously in 1992, a massive specimen weighing 31 pounds and standing nearly 10 inches high. The crystal skulls aren't ancient Mesoamerican artifacts, but they're still interesting as examples of 19th century craftsmanship and as evidence of the Victorian era's romantic fascination with ancient civilizations and mysterious artifacts. They tell us more about 19th century collectors and craftspeople than about ancient Maya or Aztec culture. The ancient belief that clear quartz was permanently frozen ice persisted across multiple cultures who had no contact with each other. Greeks, Romans, Chinese, and others all believed that the finest quartz came from the coldest mountains, because intense cold had frozen it so thoroughly it could never thaw. The logic seemed sound to them. Quartz was found near glaciers. It felt cool to the touch even in summer. It looked like ice, and it had ice-like clarity. This belief only gradually gave way as understanding of mineralogy developed. By the 18th and 19th centuries, scientists recognized quartz as a distinct mineral rather than a form of ice. But it took careful crystallographic study and chemical analysis to completely replace the frozen water theory. The practice of using crystal balls for divination, crystallomancy or scrying, has ancient roots and continues today. Believers claim that gazing into a clear quartz sphere can reveal the future or hidden knowledge. From a scientific perspective, there's no mechanism by which a quartz sphere could show actual visions of future events. However, staring at a clear sphere can induce meditative or trance states, where the mind becomes more receptive to intuition or unconscious knowledge. This could explain why the practice persisted. It may have psychological effects, even if the mechanism believed to cause those effects is incorrect. The supposed healing properties of various quartz varieties represent an area where traditional belief and modern science diverge sharply. Cultures worldwide have attributed healing powers to specific stones. Amethyst was said to cure drunkenness and prevent poisoning. Rose quartz supposedly healed emotional wounds and promoted love. Smoky quartz allegedly grounded excess energy and dispelled negative vibrations. Scientific testing has found no measurable therapeutic effects from wearing or holding quartz crystals beyond placebo effects. Quartz does have real physical properties: piezoelectricity, optical qualities, thermal stability, but these don't translate into the healing properties often claimed. That said, if someone feels better while wearing a particular stone, whether through placebo effect or genuine psychological comfort, the subjective improvement in their well-being is real, even if the proposed mechanism is not. The belief that quartz crystals can store, amplify, or transmit energy appears in many modern alternative healing systems. While quartz does have electrical properties through the piezoelectric effect, and quartz oscillators do regulate and sustain electrical signals in electronics, this is very different from the type of energy these healing systems describe. The electrical effects require specific conditions: correct cutting and orientation of the crystal, appropriate mechanical stress or applied voltage, and suitable circuitry. A quartz crystal sitting on a shelf or worn as jewelry doesn't generate or amplify energy in any measurable way. The idea that quartz needs to be charged or cleansed by placing it in sunlight, moonlight, or salt water represents a spiritual practice rather than a physical necessity. Quartz's properties don't degrade from use or need refreshing. That said, if these practices bring someone peace of mind or help them feel more connected to their stones, the ritual itself has value, even if the believed mechanism isn't supported by physics. Some sellers artificially treat quartz to enhance or change its color, then sell it without proper disclosure. As we've discussed, most citrine is heat-treated amethyst. Some smoky quartz is created by irradiating clear quartz. Mystic quartz and other trade names refer to quartz with metallic vapor deposited on its surface to create rainbow effects. None of these treatments necessarily make the stone less beautiful, but ethical dealers should disclose treatments rather than passing off treated material as natural. The misconception that harder stones are always more valuable has led to confusion about quartz's place in the gem world. With its hardness of 7, quartz is harder than many other gemstones, but is far more abundant than gems like emerald, hardness 7.5 to 8, or even ruby and sapphire, hardness 9. Rarity, color, clarity, and demand all factor into value more than hardness alone. Some people believe that synthetic quartz is fake or inferior to natural quartz. In reality, synthetic quartz has identical composition and structure to natural quartz. It just grew in a laboratory rather than in Earth's crust. For industrial and electronic applications, synthetic quartz is often superior because growth conditions can be precisely controlled to minimize defects and impurities. For jewelry and collecting, some people prefer natural quartz for its geological history, while others don't distinguish between natural and synthetic as long as the stone is beautiful. The persistent belief that quartz is rare or exotic likely stems from seeing spectacular museum specimens or gem-quality varieties. In reality, quartz is the second most abundant mineral in Earth's crust. Clear quartz beach sand covers coastlines worldwide. Most quartz is common, but exceptional specimens are rare, an important distinction. Understanding the difference between legitimate scientific properties and unsupported claims helps us appreciate quartz more fully. The real properties, piezoelectricity, optical qualities, crystallography, formation processes, are fascinating enough without embellishment. Quartz's role in technology, its geological significance, and its genuine physical properties make it extraordinary. We don't need to add mystical qualities to make quartz interesting when its actual characteristics are already so remarkable. Looking ahead, quartz's importance shows no sign of diminishing. In fact, as technology advances, quartz's unique properties may become even more critical for emerging applications. The ongoing miniaturization of electronics creates increasing demand for precise timing references. While atomic clocks offer the ultimate in precision for specialized applications, quartz oscillators provide the practical timing for the vast majority of electronic devices. As the Internet of Things expands, with billions of connected devices requiring synchronized timing, quartz crystal production must scale to meet demand while maintaining quality and reliability. Researchers continue working to improve quartz oscillator performance. Temperature-compensated crystal oscillators, TCXOs, now achieve stability of plus or minus 1 part per million across operating temperature ranges. Oven-controlled crystal oscillators, piezoelectrics, maintain even tighter stability by keeping the crystal at constant temperature, achieving performance approaching 1 part per billion. These ultra-precise oscillators find applications in telecommunications infrastructure, GPS systems, and scientific instruments. The search for alternative materials that might replace quartz for certain applications continues, but quartz remains hard to beat for most uses. Its combination of availability, cost-effectiveness, well-understood properties, and proven reliability makes it difficult to displace. Silicon MEMS, micro-electromechanical systems, oscillators have made inroads in some applications by integrating more easily with semiconductor processes. But quartz still dominates where the highest stability and lowest phase noise are required. In the semiconductor industry, the push towards smaller feature sizes and more complex chip architectures may increase demand for ultra-high purity quartz. As chips become more sophisticated, the purity requirements for materials used in their manufacture become more stringent. Sources of sufficiently pure quartz remain limited, potentially creating supply constraints that could affect the industry. Climate change may create new challenges and opportunities for quartz applications. Increased deployment of solar panels, which use quartz in photovoltaic glass production, expansion of fiber optic networks for telecommunications, and development of more efficient LED lighting, which may use quartz components, all represent growth areas that will increase quartz demand. Water purification and sterilization using UV light through quartz tubes may expand as water scarcity increases, and developing regions seek affordable, effective water treatment solutions. Quartz's UV transparency makes it essential for these applications, and global demand for clean water continues to grow. In scientific research, quartz continues enabling new discoveries. Ultra-low expansion quartz glass helps create telescope mirrors that maintain nanometer-scale precision. Quartz windows allow scientists to study reactions at extreme temperatures and pressures. Quartz crucibles enable growth of new semiconductor materials. The combination of thermal stability, optical properties, chemical inertness, and well-characterized behavior makes quartz invaluable for research applications. Synthetic quartz production technology continues advancing. Modern hydrothermal growth facilities produce larger, more perfect crystals with better control over impurities and defects. Understanding of growth mechanisms improves, allowing optimization of production processes. As demand increases, manufacturers invest in expanding capacity and improving efficiency. The geological understanding of natural quartz deposits advances as well. New exploration techniques help identify previously unknown reserves of high-purity quartz. Better understanding of formation processes guides prospecting efforts. As easily accessible deposits are depleted, mining companies work to extract quartz from more challenging geological settings. Sustainability concerns may affect future quartz mining and processing. Extracting and processing quartz requires energy and can create environmental impacts. More efficient processing methods, recycling of quartz from electronic waste, and sustainable mining practices will likely become increasingly important. The industry may face pressure to reduce its environmental footprint while meeting growing demand. In the realm of gems and collectibles, quartz will likely maintain its popularity. The variety of colors and forms, combined with relative affordability for most varieties, ensures ongoing interest from collectors and jewelry buyers. Rare varieties like natural citrine or fine chrysoprase may appreciate in value as supplies are depleted and demand from collectors increases. Quartz's future in horology, watchmaking, appears stable. While smartwatches have captured significant market share, traditional quartz watches continue to sell well due to their reliability, accuracy, and affordability. The quartz watch market serves billions of consumers worldwide, and replacement cycles ensure ongoing demand for movements and components. Emerging technologies may find new uses for quartz's unique properties. Quantum computing research sometimes uses quartz components for their thermal stability and well-characterized properties. Photonic integrated circuits may employ quartz for optical applications. New sensor technologies might exploit piezoelectricity in novel ways. One certainty is that quartz's fundamental properties, its crystalline structure, piezoelectricity, optical characteristics, and chemical stability, will remain unchanged. What changes is our understanding of those properties and our ingenuity in applying them to solve problems and create technologies. Future applications we cannot yet imagine may one day join the long list of ways humanity has used this remarkable mineral. From the first stone tools shaped millions of years ago to the possibility that quartz might help enable quantum computers or advanced photonics, the story of human technology is intimately connected to the story of quartz. This partnership between people and silicon dioxide has lasted longer than any other material relationship in human history, and it shows every sign of continuing far into the future. We've journeyed from the atomic structure of quartz to its role in cutting-edge technology, from Stone Age tools to quantum computing possibilities, from ancient myths to modern science. Along the way, we've discovered that this simple combination of silicon and oxygen, the two most abundant elements in Earth's crust, creates one of nature's most versatile and valuable materials. We've seen that quartz comes in a rainbow of varieties, from purple amethyst to pink rose quartz, from golden tiger's eye to banded agate. Each variety tells a story of the specific conditions under which it formed, the impurities it incorporated, and the geological processes it experienced. We've learned that quartz crystals can take thousands to millions of years to grow in nature, yet we can synthesize them in weeks in laboratories. We've discovered that the largest quartz crystals weigh tens of tons, while the tiny quartz oscillators in our watches and phones contain crystals smaller than grains of rice. We've explored how ancient civilizations revered quartz for both practical and spiritual reasons, how they shaped it into tools and ornaments, how they believed it held special powers, and how some of those beliefs, while not scientifically accurate, reflected genuine observations about quartz's unusual properties. We've traced the discovery of piezoelectricity by two young brothers in Paris, working with simple equipment but keen observations, and how their discovery eventually transformed into the technological foundation of modern timekeeping and telecommunications. We've examined quartz's crucial role in industries from glass manufacturing to semiconductor production, from fiber optics to petroleum extraction. We've seen how something as common as beach sand and something as specialized as ultra-pure synthetic quartz are both forms of the same fundamental material, serving vastly different purposes. We've looked at spectacular museum specimens and record-breaking crystals. We've debunked myths about crystal skulls and explored the gap between traditional beliefs and scientific understanding. And we've considered how quartz will continue serving humanity far into the future. Through it all, one theme remains constant. Quartz, in all its forms and applications, represents a unique intersection of natural abundance and exceptional properties. It's common enough to be found on every continent, in every environment, yet specialized enough that ultra-pure varieties command premium prices and enable technologies that seemed like science fiction just decades ago. The silicon and oxygen atoms that compose quartz are nearly ubiquitous in our rocky planet, but arranged in quartz's particular crystalline structure, they create something extraordinary. From the six-sided prisms that fascinated our ancestors to the precisely cut oscillators that keep our digital worlds synchronized, quartz demonstrates how nature's simplicity can give rise to complexity and utility far beyond what we might expect from such basic ingredients. If you've enjoyed this deep dive into the crystalline world of quartz, please consider liking this video and subscribing to the Sleep Smarter channel for more relaxing, educational content about science and history. Your support helps us continue creating these in-depth explorations of fascinating topics. Thank you for spending this time learning about quartz. Whether you look at quartz as a scientist marveling at its atomic structure, as a technologist appreciating its role in modern devices, as a historian recognizing its importance to human development, as a collector drawn to its beauty, or simply as someone who enjoys understanding the world around them, I hope you found something here to fascinate and enlighten you. Until next time, sleep well, and perhaps keep a piece of quartz nearby, not because it holds mystical powers, but because it represents billions of years of geological history and the remarkable partnership between humanity and the minerals of Earth that has shaped our species and continues to define our technological civilization.